As promised, we said we would decide on our final procedure, in class or take home. For those of you that are just viewing on camera, four of you. So we just took a poll to determine if we wanted to take the class, take the final in class or at home. So I polled you, so I'm going to look at these. I know, so much suspense, right? I figure there have to be reasons for these things. My goal is to try to understand the reasons things are changing. I haven't quite caught up yet. We'll do it in class. So it'll be a 2-hour final in class on Tuesday at 7:45 a.m. I think what's best is to do a yes, no, maybe session on Wednesday, and I can record that for you guys. So, and put it up online. So on Wednesday, we'll rendezvous for yes, no, maybes. You can ask me about all the things that you wanted to ask me about in preparation for the final exam. There's enough people in here that would prefer the challenge. So, and I understand it. I don't make you a deal. So, if you study, if you perform diligently and look like you know something and you've turned in your test corrections and they look reasonable, nearly perfect. Of course, you don't have to be absolutely perfect, but you know, in that A range, 90 plus, I think for a take home, and you've had a week plus to think about it and plenty of time to ask questions about it, that's reasonable. If you're able to do those things, I'll give you at least a B in this class, so nobody will go below that. If you don't turn things in, if you didn't turn in projects or they're half completed and you didn't do test corrections and things like that, that's not a guarantee. So my goal is still to give most A's in this class. So I know that I've sounded a little bit harsh and I want us to push it a little bit harder this last little bit and let's put in that effort. We're right at the end, we can see the finish line. So if we can do that, the safety net will be a B. I think everybody's performed commendably, and I would like to give at least 75% A's in this class. So if we're in the right spirit of everything and we can continue to perform commendably, turn in our homework, maybe ask a question on Wednesday, then I'll feel like we've all done our jobs to the best of our abilities. So I understand this is a hard class. There is a lot to learn. This is steeped in all kinds of different methodologies, philosophies, so all kinds of different mathematical techniques that we're using, and that does make this class hard. It is overload. And that's why I think the only thing you can really do in a situation like this is try to get ahead. So if you found yourself getting submerged, lucky you, there's advanced inference classes, there's just Bayes classes, so there's a lot of different varieties of analytics classes and inference classes that you can take and try to detangle some of this stuff. Again, we still have plenty of time. So, any questions about all that? Okay, in-person exam. Thanks for your candy. Okay, let's talk about Neyman Pearson. So we're getting into this. This basically says that the likelihood ratio test gives you a uniformly most powerful test. So if I'm following truncating by using the likelihood ratio as defined in the class, so I take the null space, I maximize the likelihood over that, I divide by the maximum likelihood estimator, I bound it by some number between 0 and 1, I can calibrate that number to a probability in the null space, the maximum error that I might occur in the null space. So I can take that constant and make it mean something to me in terms of degree of belief. If you follow that, you're uniformly most powerful. What that means, your test has this property. This is a UMP test. This means that the power, and the power is the probability of rejecting in the alternative space. So this is important right here. So this concerns the alternative space. So in the alternative space, the power is higher than any other test. So beta star is the power function for some other non-UMP test. So typically you would want this, that it's actually beating it. So non-UMP test has less power in the alternative space. What's power in the alternative space? It's 1 minus the type 2 error. So it means that it's minimizing the type 2 error. So maximizing the power in the alternative space is equivalent to minimizing the error that you make in the alternative space. So that's what that says right there. I've written this down for us, that the power function beta is the probability of rejecting. So we've got some rejection region that we can define for this. So the rejection region is going to be defined by the likelihood ratio test stat. And we worked through a couple calculations like that. So for testing a null hypothesis, theta is equal to theta naught versus it's something different in the normal example where theta was taking on the meaning of the mean in the normal distribution. We looked at how far x bar deviated from theta naught with respect to the standard error. So that was the rejection region was defined by truncating that. We did a similar example for the shifted exponential and saw what different rejection regions look like. So, UMP test likelihood ratio. We're going to prove that. Almost. Now I want to point out, this isn't a complete proof of this. This proof does extend to the one-sided case. What we're going to do is start out with just the simple versus simple hypothesis. That's theta is equal to theta naught. That's just a point. So this could be a vector in space or a matrix or something like that. We'll treat it like it's a scalar, but it's just a point in space. And this is a point in space, so that's the simple versus simple. So people might say simple versus the composite hypothesis if this was a set right here that was bigger than just a point. So theta naught, null theta is equal to theta naught versus theta is not equal to theta naught. That's an entirely different test. I want to point out this test and all the claims we make about this test are going to extend to the one-sided case. So let me just make a note. Note, by taking points, I'll just say theta naught is some region, is some set. And I'll say from theta naught, this is an actual point right here. Let's just call it theta naught tilde off to infinity. And let's let theta 1 be a set where my set is going to be theta naught tilde off to negative infinity. So I'm basically just concocting the one-sided test. So if I redefine theta naught to be this set or any point in this set, versus theta 1 to be any point in this set, they don't overlap each other, they're complements of each other. We can take every claim we make from this proof and just kind of do a very mild induction and just extend every claim we make about this test to the one-sided test. So when we're testing one side of something versus the other. The claims that I make in this test are not going to hold for theta naught versus something different from theta naught. And the reason why is the likelihood ratio test is only bounded in one direction. And so what you would need to do to really take care of this two-sided testing is point that inequality in both directions. And that's how they derive the two-tail test, is they end up saying, let's just treat it as two simultaneous one-tail tests and drop the error rate. So instead of testing at 5% on one side, you might test 2.5% and 2.5%. And that'll make a test that's unbiased. Just keep in mind, we didn't actually adhere to the likelihood ratio test stat. We did it twice, and that's not the same thing. So you do not get all the same good properties i.e. additivity, that if you move farther away from something, the p-value goes down. It turns out in the two-sided case, in the interval case, which is even more devious, and that's why they probably don't teach it to you, it's totally wildly incoherent. That I can take an interval like this and make it bigger. So it subsumes the old interval and the p-value goes down and then it goes up. So it's not monotone. Okay, and that's repercussions of the point test and the interval test. If you want to know more about that, I'll teach it to you in May's class, Stat 5444, and I'll do a more thorough treatment because I don't want to just say this thing is just terrible without giving you an alternative. And I don't think we have time to go through all of it. But just keep in mind, everything we say in this proof about Neyman Pearson holds for the simple versus simple test. It extends to the one-sided test, but for it to adapt to the two-sided test, we have to build in a constraint, the unbiased constraint. Basically, we use the one-sided test on each side of everything. And we think, oh, that should just have the same properties, right? Just shove this thing in that box and everything should be good. What I really think is testing theta naught against anything on the real number line is ridiculous. That is not the question you meant to ask. So that's probably what we're really arguing about, is what question did we even mean to ask in the first place? So I'll treat that case next fall in May's class. If you want to come out, hang out, just for those lectures, let me know and I'll let you know when I start talking about that stuff. Okay, Neyman Pearson, simple versus simple. Or by induction, one-sided tests, not two-sided tests, without the constraint. Okay, we're going to prove this thing that our test, by following the likelihood ratio, is going to be uniformly most powerful, i.e. we're going to prove that by following the uniformly most powerful test, our power function is going to bound all other power functions belonging to other tests. If there's a power function that looks like it's the same, it also adheres to the likelihood ratio test stat. So if I can conjure a test that's uniformly most powerful, it adheres to the likelihood ratio test stat. So that's if and only if. Let's just look at this. I've written down the if conditions for everything. We're going to have to say two things about the thens right here. But here's my setup. If this condition, 1, is true, X is in the rejection region, so my rejection region, that's what that denotes. This is the complement to the rejection region, so I could say X is not in the rejection region or X is in the complement to the rejection region. Same thing. So X is going to be in the rejection region if this criterion is true. So this defines the rejection region. This is all in your book. Does that look familiar? Kind of. What is this? What is this criterion? This mystery criterion?
Well, it's like the likelihood ratio if it doesn't move things.
Yeah, it's a adjustment to the likelihood ratio test. This is the LRT. So just have a look real quickly. I'll erase this in a second. But this is just f of x over the null space, theta naught. There's only one value to plug in there, so my maximization just takes that function, plugs in theta naught. I can maximize real easily. In the alternative space, it's just one point. So I plug that thing in there. And so in this thing, it's going to be bounded by 1 over k. K is going to be positive, so this is positive. So this is a criterion that lives between 0 and infinity, right here. So the bigger the number is, the more support there is on the null. The smaller the number is, closer to 0, the less support there is on the null. So this is just like the likelihood ratio test stat, but instead of dividing by the maximum likelihood ratio in the denominator, I've only put in the maximum under the alternative space. And so instead of, if I ended up unioning that with the maximum over the null space, then this number would be bounded by 1. Since I'm not normalizing it, it's bounded by anything positive. So that's something we mentioned several times when we were talking about the likelihood ratio test stat. So the book decided to deviate and not tell you. So I didn't even notice that they didn't tell you until somebody pointed out. They never mention it in the book that that exactly is the likelihood ratio test stat. So they want you to make that leap for yourself. That this really is that. There's a problem in the back of the book in chapter 8. I don't remember exactly which one it is, but they allude to it. And they ask you to show this correspondence. So if you're missing it in the book, it's because they reserved it as a problem for you. But basically, I think just some simple rationale would show this thing's always positive right here. The closer to 0 that is, the less weight you would put on the null hypothesis in terms of believing it's true. In the breakpoint, instead of 50-50 would be at 1. So if this is 1, that means that you believe in them the same in terms of their likelihood measures, and above 1 is going to start supporting the other hypothesis. So that's what that is. So this is LRT in disguise. For the simple versus simple case, it's LRT, and for the one-sided case, it's LRT. So all your decisions are always made on the boundary where you're making the decision to cut the space. So you have the most power to always determine everything right there, because it has all the data on both sides and everything. So where else will tell you the most information? Okay, this condition says that we're not, it's the complement. So this is LRT2, this is the other thing. And this is just the size of the test right here. So we're gonna lock this down and say we know what the power is. So the probability of rejecting in the null space, so this is the power function in the null space. There's only one point. We're going to say we know what it is, it's alpha, so that's that 0.05 thing. Most people point to. I always pick my alphas to always be 0.07. So I'm thinking really hard about changing that threshold to 0.073. I might write a paper on it one of these days. So it's just as ridiculous as any other number out there. So, okay, maybe 0.1. So, size of the test. So we're going to lock that down and fix it. So here's my criterion. If I follow the likelihood ratio test stat, and I've got my size of my test, my max power, in the null space, it's equal to alpha, and it's going to be locked down. I want to present you with another definition real quickly, because they do use this in the proof. It's not necessary to use in the proof. I'll address this at the end of the proof. But the level of a test, so the size of a test, the size of the test looks like this. Maximum over theta in the null space of my power function is equal to alpha. So that's what we usually talk about when we're talking about the size of a test. In the level of a test, at least the way your book talks about it, my experience is most people outside of Casella and Bergerland use these terms interchangeably. So the level of the test is usually defined by this. Max theta in the null space, beta theta, the power function is bounded by alpha. And so if you can't lock this down and make it exactly alpha, you might be able to say something about a bound. This does not seem important to me. So if something is level alpha in the simple versus simple test, it's also size alpha. There's only one point. There's nothing to bound anything. So it's going to take on some value. Why not just say what value it takes on? So there aren't too many choices. So the reason the book brings up level is they say if I drop the power, or if I drop the alpha level in the null space, all you're going to do is raise the power in the other space. That's the trade-off. That's that teeter-totter effect. So they're saying If I end up decreasing this alpha, I'm only going to get more powerful in the other space. So let me just forget about that. I'm going to say size everywhere in this proof, and then we'll come back and say what the part was about level. It's not meant to confuse you, but it probably is, and it's probably the one thing you're going to attach yourself to, just because I talked about it for 10 seconds. So don't worry about it for now. It's not that important. Level and size are the same for the simple versus simple test. And in the last part of the proof, they even invoke that and tell you that. So it's probably not necessary to even talk about level. So I'm not going to have you distinguish that. If you can't remember which one is which, and you use them interchangeably, you'll be just like everybody else. Okay, so what do you think the then condition is? So if this is true, then what? Anybody read this yet? No? Do you know?
Yeah, so I think the big one would be that it's uniformly most powerful.
It's UMP. That's basically all of them. So it says, if 1 and 2 are true, hold. Oh, and let me just write down. I'm just going to write something down. I'll need that space in a second. If 1 and 2 hold, this is what I want to write down. Let's define a test real quickly so that we can use this in our notation. The book does this as well. Let delta x be equal to a 1 or 0. This is going to happen if f of x given theta 1 is greater or equal to k times f of x given theta naught. It's the same condition written over to the right. So I'm basically just going to say an indicator. I'm going to assign an indicator if we're going to reject the null. So in my indicator, it's going to be a 1 if we reject the null, and it's going to be a 0 otherwise. So I'll just write down otherwise. It's just the flip of it. It's this condition right here. So I'm going to have a test that takes on that right there, and we're going to show that this test is uniformly most powerful. We're also going to let this test have size alpha. So this is a test. This is my rejection region. It's going to be size alpha. So it's calibrated to do that. So if 1 and 2 hold, I'm going to say our test is UMP size alpha. So basically what Jared said. The B is just that, the only if condition. It says every test that's UMP, if it exists, adheres to this. So this is the only gig in town for finding that test. If there's a test, there exists a test. That satisfies 1 and 2. And is size alpha. Then all UMP tests satisfy 1 and 2. So I'm back to being a math major all of a sudden. So it feels just like that, right? Might as well get one of these in. So if and only if. So we'll prove this. Basically, it's the same proof in both directions. So if you understand what the condition is, we can express something with equality, and that is an if and only if statement. But we'll walk through them both sides gently. Any questions about all this? We hear the likelihood ratio test, or at least something that's 1-to-1 with the likelihood ratio test stat. It's size alpha, it's going to be UMP. That's kind of cool. I kind of like all this. So I want to remind us what we're doing here, or what Neyman and Pearson were doing. What do you think their whole goal is? Anybody ever studied the history of statistics and where all this junk came from? This one, the estimation stuff's pretty good. I like that stuff. So this is okay. I don't mind testing a point against a point. I think that's totally reasonable, you know? So Neyman and Pearson. So baby Pearson. Does anybody know his first name? Egon, yeah. One of the coolest names ever. Does anybody know anybody named Egon? So name your firstborn child Egon, just for prosperity's sake. So Egon and Neyman got together and were trying to understand what Fisher was talking about. So Fisher had come up with the p-value. And Fisher was saying p-value is the error rate. And it's not true. So the procedure is this. So coming up with p-values, uniformly most powerful ones, the procedure is you derive your test stat out of the likelihood ratio test statistic sort of procedure bill. So you come up with something UMP. Fisher hadn't concocted that himself. So I suspect he probably knew things like it. So he's coming up with the right stuff for some reason, the right test stats to test on. So he had some inclination as to how to get them in the first place. How we got them, I'm not sure I know. But Neyman and Pearson give us a procedure for coming up with something uniformly most powerful, and they wanted to address this question of what is the meaning of p-value. So Fisher was saying that it was the measure of the null hypothesis. And Neyman and Pearson were saying not so fast. I think you could address it that way in the simple versus simple case, or in the one-sided case in a lot of cases. A Bayesian's posterior probability will be a lot like the p-value, but that doesn't hold in the short test. There is no semblance of agreement between Bayesians and non-Bayesians, and the p-value is nothing like a measure on the null hypothesis. However, if you pre-specify alpha, and if p ducks alpha, then your probability of making a type 1 error, rejecting the null when the null is true, is alpha. In Neyman and Pearson, we're trying to help Fisher by saying exactly what the understanding of the p-value could be in all cases. You're really calibrating alpha. And Fisher went berserk. So Fisher's like, so the answer's alpha, it's always alpha. How sure am I it's alpha? The error rate's alpha, what about p? Small p and big P, you know, p .049 and p .00049 shouldn't mean the same things. So they're different degrees of belief. Unfortunately, Fisher couldn't reconcile that comment, and he wasn't able to go any farther with it. And so Neyman and Pearson talked about this as a procedure for a way to understand the p-value thing that people were doing. I want to point out also, Neyman and Pearson never blindly followed this. Never once. And they'll even talk about it. I've never done this. So I just wrote a paper on what it all meant. And so if you go out there and you just collect some data, do this test, and you get a p and it ducks some alpha, and you're just like, well, I just rejected, there's not a lot of insight there. So it's more like what's different between the two processes. Explain all that to me. And so there's probably a lot more insight than just saying p was small. So I don't think they were that type of statistician. We'll talk more about that next time. Let's see if we can carve our way through this proof a little bit. So let's look at the master equation. So this equation is key to understanding the proof. And in the book, they just kind of state this. They say this is true, and if you skip through this line and don't put any thought, you miss the whole point of the proof. So this is greater or equal to 0. This is going to be delta x. This is my uniformly most powerful test. It's that test, or sorry, we will prove it's uniformly most powerful. I just happen to know. So it's this test, adhering to the likelihood ratio test stat. So delta x minus delta star x. This is some other test. And I'll say it's size alpha. The book actually lets this one be level alpha, and all it does is if I end up making alpha lower, because I'm only bounded by alpha from above, it makes the power bigger. It's just that trade-off, that obvious trade-off. So I'm just going to say size, again, even though the book says level right here. That it could be smaller, and it's just going to make the test more powerful. Okay, so delta x is this test, this is some other test. So we're imagining some other rejection region out there. You came up with some other rule for rejecting. So it has a different R attached to it. Times, this is going to be fx given theta 1 minus k fx given theta naught. X's come from F, just like always. This is our condition right here. You need to verify this to yourself. So if you come across an equation like this, you check it. Is it true? How do you check this? You just sit back and think about it, right? You stare at it. Yeah. Hey, check it. I guess you guys like the stare at it sort of thing. Burn a hole through it. Don't look at Scotland. Somebody throw out a suggestion. How to check this real quick. It's easier than you think. How many things do you have to check? Huh? Is it obviously true? I remember I looked at this and thought, huh? It is? Why? It's got to be a reason. So meow meow. Do you want me to tell you? It's ready. Jake?
So if if our test indicator is 1, that means that the that whole term is going to be either 1 or 0, because either the second test is on or off, making that 1 or 0. And if our indicator is 1, that means our second term also has to be positive, because that's the condition for our indicator to be 1, meaning it's either, the product is either 0 or 1, and if it's not true, then it's either going to be 0 times a negative or negative times a negative, which is a positive.
Yeah, everybody got that, right? So here's what he said. There's only 4 things you need to check right here. This could be a 1, that could be a 0. This could be a 1 and a 1. This could be a 0 and a 1. Or that could be a 0 and a 0. All things you can check real quickly. This one's real easy to check. That's the equal sign. 1 minus 1. Last time I checked it, that's 0. Multiply by something, not going to help it. So it's a magical number. Same here. Right here. 0 minus 0, it's still 0. So all you have to do is just check the 4 cases on all of this. So 1 minus 0, that's positive. So this is going to be a positive right here. Let's look at that thing. So when that's a 1, this is positive. So this is bigger than that right there. So this thing is positive, so that's positive. So 1 minus 0 is positive times something positive. Super. So this case, when this is a 0, this test, we know that's negative. So if that's a 0 and that's a 1, this is negative 1 times something negative. So that's positive. So good job. So you just check the cases. 4 possible cases. The only thing those indicators on the front can be are either a 0, a 1, or a minus 1. You can examine each case. So it doesn't matter what this is for that to be positive or negative. It only depends on the value given. So that's true. This is what we'll use to prove everything. part A of the proof. Here's our master equation. So we're going to go from here. We're going to use this the whole way through everything. So let me just integrate over this equation. Integral delta x, delta minus delta star x by 2s, indicator values. So I probably should have said this is indicators for some other test. It's just a different rejection region. F of x, given theta 1 minus k, f of x, given theta 0. dx. Just so you know, I'm integrating over the entire space. So of x. So this is still positive. I add up a whole bunch of positive stuff, it's positive. So I want to just remind us, there's something I erased off the board. The expectation of an indicator is equal to the probability of whatever event that indicator is indicating. So this can be broken up into 4 different integrals over integral indicators. So just notice if I expand this into that, there's going to be 4 terms that appear. Each term will involve something that looks like this. So there's 4 terms that look like integral, I'll say delta x times f of x given theta, and it's going to be either theta 1 or theta 2. So I'll just put an I down here. D theta, and this is going to be equal to the expected value of this indicator right here. This is under theta I. I'll just be specific about it, that there's a theta I in there. I can either be 1 or 2, or 0 or 1. Just these 2 hypotheses that we're entertaining. So that's the expectation of an indicator. This is going to be the power function for that indicator. So that's the probability of that thing. So expectation of an indicator is the probability of that event. Just think about it, Bernoulli model. So this is the power. So that's for this particular test. I could do something similar, and I could give us some notation like that. Delta star, I'd have a delta here, and I'd put theta star right there. So all the deltas don't have stars on them, all the delta stars coincide with power functions with the star on them. Christina?
Why would the integral with respect to theta?
The integral, it's not. Yeah, that's crazy. X. So still, so I'm just expanding these terms, this into the 4 terms, so sorry about that. X. Yeah. So that's the power function. So this is going to break up into 4 different power functions. I'll let you work this out and do that expansion for yourself, but it's going to look like this. Beta, theta 1, minus beta star, theta 1. Give myself a little bit of room. I'll just write down this beta star theta I here. This is going to be beta theta I. That's this one against that. Then this one against that is that one. And this is going to be minus k beta theta 0 minus beta star theta 0. So just a little bit of simplification. So that's this one against that right there, and this one against that is that one. So just a renaming of this integral in terms of its power functions. So that's that. Okay, so quick obvious thing. This right here, do we know anything about this? We know what this is. I didn't write it that way. This is beta theta 0. That's the power if theta 0. Probability of rejection. So that's alpha. What about this one? I said it's alpha. So it's also size alpha. If it were level alpha, I'll just throw this in right here. This is positive. Right here. So this is alpha minus something smaller than alpha. So this could have been less than alpha. So mathematically that's true. It won't change our results. So this thing is going to be bounded by b theta 1 minus b theta star, b star theta 1. Right here is greater than 0. So if I did take that to be level alpha, that would just be something less than alpha, and I would have this to be the bound. If I picked it to be size alpha, which it is, so the book doesn't say that until the second part of this proof, then we have the equality. I would say there's an equality, but if you wanted to talk about something and compare it to something that had power smaller than alpha in the null space, then our result is still true. So they're right. No big. So at the end of the day, that just says beta theta 1 is greater or equal to beta star theta 1. This was our test adhering to that, and this is some other test, so it's UMB. Voila. You could probably convince yourself through a minor induction. If I marched the theta naught to the right and I marched the theta 1 to the left and did the proof again, I'd get the same result. And if I marched the point to the right a little bit more and I marched theta 1 to the left a little bit more, I get the same result. It'd be the same proof over and over again, so I can induct and extend that to the one-sided case. You need to add a constraint to talk about the two-sided case, the problem that everybody talks about that doesn't have the beautiful properties of this. Not exactly the same. It does manage error rate. But P doesn't mean what you think. So U and P. Let's go the other direction. Same thing. Our test, delta X, adheres to the likelihood ratio test stat. Delta star is some other test. Here's what we're going to say. We're going to let, so this is part B. Let delta star X be size alpha. Again, they say level alpha. I say size. They're going to change it to size in just a second anyway. So be size alpha. And I'm also going to say, and let it be U and P. And I'm going to consider my old test. Delta X is the one that follows the likelihood ratio test stat. So delta X still has the exact same meaning. I've defined the rule for you. It's likelihood ratio test stat. I'm just saying delta star is UMP. So the mathematical line of thought is to show that delta star X is delta X. So that's the normal way to do this sort of thing. So I assume that it's also UMP. There's some other test out there. And then I show, oh, it has to be this other test. So that's what we'll show. So if you don't like that, don't take advanced inference, because that's what the whole class is going to be. There's lots of proofs just like that. So if one direction is good enough for you, that's good enough for me. So I probably won't test you on both directions of this. I'd say a PhD student in statistics, though, should be able to discern this and understand how a uniqueness proof works. Let's just do it. So we still have this delta X minus delta star X f of X given theta 1 minus K f of X. given beta naught. Dx is greater than 0, which implies that beta 1 minus beta star beta 1 minus k beta naught minus beta star beta naught is going to be greater or equal to 0. Now we know something about this. What do we know about those? Okay, I'm going to give you a hint. Oh, go ahead.
They have to be equal.
They have to be equal. Why?
Because you said delta star was inversely goes power.
Yeah, so it's UMP. So these are equal to each other. We'll pick up with this next time, just so we don't rush through this. But these are equal to each other because they're both UMP. And this is where the book ends up saying, okay, this is alpha. This is level alpha right here, but then they say, well, we're really testing the simple versus simple thing, so enough of the level, let's call it size. Because it's just 1 point, and level in a 1 point test has to be the same size. That kind of annoyed me when I finally got to that part of the proof where I was like, I just spent 3 hours thinking about that. You know, why didn't you just tell us this also is size? It is. So this is going to be equal to 0. So this whole thing is not going to be bounded by 0, but it's really going to be equal. We'll come back next time, relook at this equality, and we'll say what it says, but what it really says is if this thing is equal to each other, then, and this is equal to 0, then delta x has to be equal to delta star x. So come back next time and try to answer this question, why are those equal? We know why those are equal, because they're both size alpha tests. These are equal because we just said that's UMP, right there. So go back and ponder that for a second. If this whole integral is 0, everywhere on x, and this is a continuous function, then these two things must be the same as each other. Now they do put a little caveat, that's on all measurable sets. There could be some little tiny pocket, some little point x, where this isn't 0, it's something different. But that doesn't extend to more than just a minor blip in space, an anomaly, it doesn't extend to a set. So anything you integrate over with that property has measure 0. That's what that means. So could happen, but you'll never measure it. So lots of unmeasurable things happen. So in our whole land of measurability, every random variable that we get from a continuous distribution happen with probability 0. I'll let you think about that. So things do happen, but compared to the rest of the universe, you don't expect them to happen. That's what that means. So these are identical to each other. So this test is that test, and that test follows the likelihood ratio test. So all UMP tests are adhering to the likelihood ratio test statistic if they exist. Let's come back next time, talk about the BAS paper, the ASA paper, where all this sits. I'll give you a prelude as to what a Bayesian does and give you some notation. But it'll basically just prompt you to think about this more in the future, I think. So, but what I would like you to do for the exam is be able to work out likelihood ratio tests, work out the rejection region, and then if I asked you to pick a constant to calibrate the probability, you would have to say how you might do that. So, does anybody know what the thresholds are for a normal distribution? If I want my p-value to be at the 0.05 level, it depends on the test that we're doing. So it'll be kind of difficult to test you on that without giving you a table, and I'm totally opposed to doing that. So I don't think I'm ever gonna do that. But you basically need one of those stat probability tables and look up the numbers like 1.68 or 2.56 or 1.96. Those are all those critical thresholds. And those adhere to different levels of different tests, or sizes, I should say. Anyway, let's come back next time and try to wrap this up, but it's gonna leave you with lots of questions. And that's good. Hopefully you ask them. Anyway, I'll see you guys on Wednesday. Thanks so much.